Hello everyone, am I audible? Can you please confirm if I am audible? Hi everyone, can you please confirm? Good, I am good. Okay, very well. आकाश स्टार्ट करते हैं जल्दी से फटाफट. ठीक है. So this session we will be covering all the heat transfer formulas from conduction, pins, unsteady state conduction, your heat exchangers, your radiation, as well as your convection. Okay, everything what is required. We will also be seeing the type of questions that you might expect in your exam from heat transfer. Okay, so we will start soon. Before that, a few announcements, guys. So if you have not joined my Telegram channel, do join. It is Mechanical by Vipin Yadav. So either you can scan this QR code or you can just type in the name and you can join as soon as possible. Marathon, we are planning for Jan. Okay, for thermodynamics I will take, and other subjects will be taken by other faculty. Okay, chalo. So guys, if you are not on the app, download the app. Okay, there is so much going on the app, and on 30 and 31st we will have a scholarship test that you can join. If you are planning for GATE 2025, you can give a scholarship test and get up to 90% of the scholarship. Also, on 3rd of Jan, Richa ma'am will be coming up on tips to handle stress during GATE preparation. Okay, chalo. How can you download the app? You can download the app by, you see this link, below the video you will see this link. Click on this link and you will be able to download the, okay? Or you can scan this QR code as well. You can scan this QR code, it will be directed the app, and you can download the app, you can go ahead. Okay, chalo. Also, if you are planning to join for GATE 2025 and 26, batches are already started. Thermodynamics is starting from today. Okay, so I will be taking thermodynamics from 9 a.m. today. So now it is the right time to start to prepare for GATE 2025. Start as soon as possible. ठीक है, चलो start करते हैं. Let's start. Okay, let's start with the very first topic that is conduction. Now guys, the story of conduction starts with what? Fourier's law of conduction. Okay? And it says that the heat transfer is directly proportional to the temperature gradient and the area in the direction of the heat transfer. Okay, in the direction. So if this is the direction of heat transfer, this area you are going to take. So this area you are going to take. This area you are going to take. So therefore, heat transfer is given if you remove the proportionality constant minus Ka dt by dx. Okay, and why do you use a minus? Because temperature always decreases in the direction of heat transfer. So dt by dx will always be negative. It will always be negative. So to make it positive, we use a negative sign here, so that this is to satisfy the second law of thermodynamics. To satisfy the second law of thermodynamics. ठीक है, चलो. Now guys, as you all can see, we have generalized heat diffusion equation in Cartesian coordinate, in cylindrical coordinate, and spherical coordinate. What you need to remember is at least Cartesian and cylindrical you need to remember. Okay, so this is dt, but this is three-dimensional with heat generation unsteady. यानी कि this is a generalized equation. This is the generalized equation for Cartesian coordinates, and this is the generalized equation for cylindrical coordinate. This is the generalized equation for spherical coordinate. Okay, now let's start with, first of all, we have three kind of cases that can happen. First is one dimensional, no internal heat generation and constant thermal conductivity. First of all these cases are steady state. All these cases are steady state. Unsteady state we will talk later. Okay, so it is one dimensional, no heat generation and constant thermal conductivity. In this we will see Cartesian, cylindrical and spherical. Then next we have one dimensional, no internal heat generation, and variable thermal conductivity. Variable. In this only Cartesian we are going to see. Then we have one dimensional with heat generation and constant thermal conductivity. So these are the all three cases. Then we have applications, which is composite slabs, critical insulation, and so we are going to see them one by one. Okay, chalo, let's move ahead. Let's move ahead with the first case. The first case is, look, first of all the cases we are going to discuss is steady state. Okay, steady state, one dimension. So when I say steady state, that means this goes to 0. When I say one dimensional, that means this goes to 0. When I say no internal heat generation, means this goes to 0, and it is the case of constant thermal conductivity. Okay, so now this is the generalized equation. This is basically a governing equation for this case, and only in this case you can draw resistance network. Not in any other case you can draw resistance network. Only in this particular case you are able to draw resistance network. Okay, chalo. Now once you integrate it once, you will get this, and then again you integrate, you will get temperature distribution. So temperature distribution is linear. Okay, temperature distribution is linear. That means if this is T1, this is T2, so this should be your temperature distribution, and your slope is constant. That means dt by dx is constant. Okay, now I need to find out C1 and C2, and therefore two unknowns, two boundary conditions I require every time. Okay, now what kind of questions you can expect? The first type of question in this case you can expect is find out heat transfer. So they will give you T1, they will give you T2, they will give you K, and they will give you area as well, and this is the thickness. Okay, so you will be able to determine the heat transfer by this equation in this particular case. Okay, next is when there is a fluid on both sides. So there is fluid 1 on this side with T infinite 1 temperature on this side, and heat transfer coefficient H1. Here T infinite 2 on this side and heat transfer coefficient on this side. Okay, so you will be able to draw a resistance network, and you can determine the heat transfer by this equation. Okay, so T infinite 1 minus T infinite 2 divided by the total resistance. Now you can also break this. Okay, so you can take these two resistances, you can take from T infinite 1 to T1, and only this resistance you can take, or you can take is equals to T1 minus T2, where T1 is here, T2 is here, upon L by K. This also can be taken. Good evening, Ishwar. Good evening. Okay, so you can break it into different resistances. For example, T1 is asked, so you can take this and this equation, and only T1 is unknown, you can find out T1. So depending upon what you need to find out, you can break the circuit, break the resistance network, and find out what is unknown. Okay, chalo. Next is steady. Now we have cylindrical coordinate. Same case, steady state, one dimensional, no internal heat generation and constant thermal conductivity, and cylindrical coordinate. What do you have? Cylindrical coordinate. Now first of all we are assuming only radial conduction. That means there is no heat transfer in this direction. In this direction heat transfer is 0. Only in the radial direction heat transfer is not equal. That means heat transfer is only happening in radial direction. So you have this equation. Now when I say steady state, that means this goes to 0. One dimensional means this goes to 0. No heat generation means this goes. So you will have this equation, you will integrate it once, you will get this, and this is your temperature distribution. And what is this temperature distribution? It is logarithmic. It is logarithmic. Now again, what kind of questions can be asked? The first question that they ask is find out the rate of heat transfer. So they will give you R1, they will give you R2, they will give you thermal conductivity, and you will be able to find out heat transfer. by this, and this is your thermal resistance in cylindrical case. Okay. Now next is again they will ask you heat transfer, but inside and outside fluid is given. There is some fluid this side. This whole cylinder is basically it is occupied with fluid, and also inside there is fluid going on. Okay. So in this case you will be able to find out heat transfer by this equation. So this is the this is the resistance through this fluid. This is the conduction resistance in the thickness. Okay. So first of all there is convection resistance, then conduction resistance, then convection. These three resistance you will be able to see in this particular case. Okay. And area is 2 pi r1L, 2 pi r0. Okay. Now there is one special case that comes in the cylindrical, and that is that heat transfer is happening in axial direction, yani ki in this direction. In axial direction heat transfer is happening. In radial it is not happening. In axial. Usually the case that you see is radial direction, but there is a special case that in axial direction, yani ki in the axis, in the axial direction heat transfer is happening. So in this case you are not going to use a general cylindrical equation, you are going to use Cartesian equation. And this is the general heat transfer. How to find out heat transfer is this T1 minus T2 L by Ka. So it is a special case. A lot of students get confused when they see axial heat transfer. Okay. So when heat transfer is happening in the axial direction or Z direction, you are not going to use cylindrical heat diffusion equation. You are going to use Cartesian heat diffusion equation. Got it? Chalo. Now next is spherical coordinate. So first of all, steady state means this goes to 0. Internal heat generation is not there. That means this is equals to 0. And one dimensional means these two things goes to 0. Now the only equation that is left with you is this. Once you integrate it, you will get this. And second integration you will get. And this temperature distribution is hyperbolic. Okay. So now two boundary conditions you need, because C1, C2 you need to calculate. So first boundary condition is at R is equals to R1, T is equals to T1, at R is equals to R2, T is equals to T2. You are going to use these boundary conditions and you will be able to determine heat transfer in this particular case. Now this is the thermal resistance of conduction for sphere. You all know this, right? And second is find out rate of heat transfer if inside fluid and outside fluid is given. So this case will be similar to the case of cylindrical coordinates. Chalo. Now guys, next very important case here is steady state is there, yes. One dimension is there, yes. No internal heat generation is there, yes. But you have variable thermal conductivity. What do you have? Variable thermal conductivity. So you have this equation in this case, because you see one dimensional means in Y and Z it is 0. No internal heat generation means Q generation is equals to 0. Steady state means your right side is also equals to 0. Now you have this, but here I can't take K out because K is a function of temperature. And in this particular case it is given that K is linearly dependent on temperature. So it is a linear variation of conductivity with respect to. Now in this, if K, this K can be, this beta can be positive or negative. So if beta is positive, then this graph you are going to see. If beta is negative, then this graph you are going to see. Okay. Now how you are going to calculate heat transfer in? So you see when this K is constant, then you use simple equation. What? KQ is equals to T1 minus T2 L upon K. But in this variable thermal conductivity case, you can't take K. You have to take K mean. You have to take K mean. And what is K mean, sir? K mean is K1 plus K2 by 2. Now K1 is what? At initial temperature T1, K2 is at final temperature T2. Or you can also write K mean as this, where T mean can be written as this. So this case is generally, now they are asking this case, and you need to know how to calculate K mean. So this K mean can be calculated using this equation, where K naught will be given to you, beta will be given to you. You just need to calculate T mean using this equation. You can put it here and you can calculate your heat transfer using this equation. Okay, chalo. Now the next case is with heat generation. Steady state, one dimensional heat generation is there, and K is equals to constant. K is equals to. So bhaiya, steady state means this is equals to 0. One dimensional means this is equals to 0. So you are left with d square t by dx square plus q generation by k is equals to 0. Yes. Now, if you integrate it once, you will get this equation, and this is the temperature distribution. And you, as you can see, temperature distribution is parabolic. Temperature distribution is parabolic. Okay. Now, when you have this heat generation case, now there are two cases. First is thermal non-symmetry, and the second case is thermal symmetry. Okay. The first case is thermal non-symmetry. So what is thermal non-symmetry? So let's say there is some heat generation in this, and whatever heat is generated, it is going out from both sides. Okay. And when it is going out from both sides, this Q right is not equal to Q left. This Q right is not equal to Q left. So Q right, let us say, is greater than Q left. Q right is greater than Q left. You can say, okay, so Q right is not equal to Q left. Okay. Now what you are going to do, this is your boundary condition. Now what are the characteristics of this? First of all, heat flux leaving from both sides. Temperature profile is parabolic, yes, but it is non-symmetric about center plane. That means the maxima you will not be getting at the center. Maxima you will be getting either on the right hand side of center or on the left hand side of center. Okay. Now let us say here Q left is less. So you will be getting a maxima at this side. This Q left is less. Therefore, here you will be getting a higher temperature, and maxima will be on the Q left side. So maxima will always be between center and the side where heat transfer is less. So Q left is less, so maxima will be on this side. Here Q right is less. So maxima is between center and the right side. Heat transfer will always be between the center. Between means not exact between, but it will be somewhere between the center and the side where heat transfer is less. For example, Q right is less, here Q left. Now, in this temperature distribution equation, when you use these boundary conditions, you will be able to determine C1 and C2. And then, in order to get this maxima plane, you can get dt by dx is equals to 0, and the x that you are going to get, at this x you will be getting your T max. So it is a simple question. You just have to calculate C1 and C2. Okay, that's all. Now the next case here is, okay, some conclusions: maximum temperature in the slab always between center plane and the side with a higher temperature. Flusk leaving from side having lower temperature is always higher. So you see here heat flusk is higher, because whenever temperature is lower means heat flusk is higher, simply. Okay. And maximum plane acts as insulated plane, and heat is transferred to both sides. So wherever you get the maximum plane, you see here we are getting maximum plane, means dt by dx is equals to 0. And dt by dx is equals to 0 means is insulated. So this is insulated, then from this plane both side heat transfer is. Now next is thermal symmetry. So it's very simple. Here what is there? Whatever heat is generated, equal heat is going from both side. Equal heat is going from both side, and maxima will be at x is equals to 0. Maximum will be at x is equals to 0. So here plus cleaving from both side is equal. Temperature profile is parabolic and symmetric about center plane. So here the first boundary condition is at x is equals to 0, dt by dx is equals to 0. So by putting in that equation, C1 will be 0. Then next, these two boundary conditions where you will put C2 will be. So then in that temperature distribution equation, you can put C1 and C2 and you will get this equation. And you simplify this, you will get this equation. So here temperature at any x is given by the function of T wall. Okay. Now what kind of questions you can expect? So you can expect कि sir calculate T center, maximum temperature, when TW is given. So as you can see here that in this equation, I need to, if I know at x is equals to 0, T is equals to T max. So if I write x is equals to 0, I will get T max here. Okay. And then I will get this equation as well. And here I can see delta T is proportional to L square. So second question can be asked, if length is doubled, then delta T increase by how many times? So as you can see, it will increase by 4 times. Okay, by using this equation. Now the next type of question can be asked is, if calculate T max, but in this case TW is unknown. So how can you find out TW? Whatever heat is conducted here will be convected here. At this point, Q generated is equals to Q lost. Whatever generated is lost both sides. Okay, so you can write Q generated in this form and this Q lost. From here you can find out TW, and once you find out TW, you can find out T max by this equation. Okay, very simple. Now next is same case with heat generation and cylindrical coordinate. So this is your generalized equation. Okay, this is your, once you finish this is done. So you can find out, once integrate you will find this, second integration you will find this, and this is a general variation. This is a general. Now again, thermal symmetry case. So thermal symmetry is, at R is equals to 0, your dt, yani ki maximum you will get here, dt by dr is equals to 0. So C1 is equals to 0, and at R is equals to 0, T is equals to C max. So C2 is equals to C max. What you are putting at R is equals to 0, dt by dr is equals to 0. You put this condition here, you will get C1 is equals to 0. Then at R is equals to 0, T is equals to T max. C1 is already 0. You can put C1 0 here. Then C2 will be T max here. So you have found out C1 and C2. Then one of the boundary condition is this as well. Okay, you can put all the boundary conditions. You will get this equation. T is equals to Q dot generation R square by 4K 1 minus R square plus TW. So again, it is the temperature at any R in as a function of TW. So if you know TW, you can find out T at any point, at any R. Okay. Now what kind of question they can ask? Find out T center if you know TW. Simply just T max is what? At R is equals to 0. So if you put R is equals to 0 in this case, you will find out T max. And from here I can see T max is a function of R square. So if radius is doubled, delta T will increase 4. Next, again find out T center, but here TW is not. So first of all, you will say Q generated is equals to Q convected. From this equation, you will find out TW, and TW once you find out, you can put in your equation and you can find out T max. Simple. You need to understand the cases first. Okay, chalo. Now composite slabs, okay. So now you can see you have, let us say, these kind of slabs. So first of all, let's say series arrangement. So as you can see, this is your body 1, this is your body 2. Here, this is your delta T by delta X, this is your delta T by delta X. And this is your series resistance network. Now tell me, can you tell me this slope is higher or this slope is higher? So as you can see here, this dt by dx 1 is less than dt by dx2. So this slope is higher, and if this slope is higher, Q is equal to, same heat transfer is happening here, same heat transfer. Q is equals to minus K A dt by dx. So if this is higher on the second slab, then this will be lower. Yani ki K2 will be lower than K1. K2 will be lower because you have to keep the product as constant. So K2 will be lower. K2 will be lower. Okay. Now in this case, you can see that dt by dx2 is lower and this is higher. Dt by dx of 1 is greater. This is greater than this. So if this is greater, K1 will be less. K1 will be less. This type of questions they are asking nowadays. Okay. Now what is equivalent conductivity? Equivalent conductivity in series case, you can write it like L upon KEF equals to L1 upon K1 plus L2 upon K2. Now what about parallel? So in parallel, you have this kind of circuit. Okay? So here heat transfer gets distinct. Heat transfer gets distinct. So in this case, your total resistance is 1 upon R1 into R2. This is your resistance. Now in this equivalent thermal conductivity can be given by this. Now what about composite cylinders? Composite cylinders. So if you see radial conduction is happening, and conduction is happening only in the direction of radius, then you have one slab like this, one cylinder like this, and other cylinder like this. This is your first cylinder, your second cylinder. So it is series connection, and you can add your resistance. But if you have axial conduction, means heat transfer is happening in this direction. So here Q will get, basically Q will get divided. Okay, Q will get divided, and therefore here resistance will be taken as Cartesian coordinate. Okay? L upon K1A, L K2A, and this will be put here. You can find out R total. Especially this is a special case of parallel connection for a cylindrical, for two composite cylinders basically. Okay. Now what about critical radius? Critical radius. So guys, critical radius, we are only talking about when you are increasing the outer radius of, so you see this is your cylinder, let us say, and you are increasing the radius of insulation. You are increasing the radius of insulation, or R naught. Okay. As you can see, when you are increasing R naught, this conduction resistance increases, but convection resistance. So conduction resistance increases, this decreases. That means maximum total resistance will be somewhere in between, and that you can find out by differentiating and putting it is equals to 0. Whatever point you are going to get, the minima or maxima will be the critical radius. So R critical is K insulation for H naught for cylindrical case, and for spherical it is 2K insulation by H naught. And when they ask thickness, then you need to find out R critical minus R out. That you can write to find out critical thickness. ठीक है, clear है? चलो, now let's go with fins. So guys, Fins is the way to increase the heat transfer by increasing the surface area. It is to, when we try to increase the heat transfer by increasing surface area. Okay, so this is the governing equation. This is the governing equation where theta is equals to T minus T infinity and M is equals to this HP by Ka. HP by K, heat transfer coefficient, perimeter, thermal conductivity and cross sectional area. Okay, and this is the general solution. Now we have two unknowns, C1 and C2. So I need two boundary conditions. So first boundary condition is this: at x is equals to 0, yani ki at this point, this is here x is equals to 0 and x increases in this direction. So when x is equals to 0, T is equals to T naught, means root temperature. Root temperature. Okay. So when you put this, x is equals to 0 you put and T is equals to T naught, then theta will be theta naught and you will get this. Now your second boundary condition will be depending upon the type of the fin. For example, if you have infinitely long fin, then your temperature, that means that at tip you have so long fin, very long fin. So eventually at the tip, temperature will be equal to the temperature of the fluid. Okay, so in this, temperature distribution equation is given by this equation and heat transfer equation is given by this. Okay, where theta is equals to T naught minus. Now second case is fin with insulated tip, yani ki at this point fin is insulated. That means at x is equals to L, dt by dx is equal to, and therefore d theta by dx is equal to. So when you put these conditions in our general equation, you will find out temperature distribution equation as this and heat transfer as this. Now let us say you want to find out temperature at the tip of the fin. So here T, what is this T? This T is the temperature at any x. So you write x here. At x is equals to L, T is equals to TL. So you write TL here. You write this x is equals to L. This will be 0. It will be 1 upon cos x. Next case is fin with uninsulated tip or convection. That means this is not insulated. Here heat transfer is happening by convection. So in this case, we use this equation. It is a very big equation, and sometimes you need to remember this equation. There is no other way. But sometimes you can also simplify it by using some assumptions. Simplify it, and you can whatever equations you had, just in this case, whatever equations you have in the insulated tip case, you assume is replaced by a corrective length. So it is corrective length. Here also you will have corrected length. Both equations give you same answer. Both equation gives you the same answer. But sometimes they specifically want you to solve with this equation. So you need to remember this equation. There is no other way. Now what is corrective length? It is LC L plus delta, and delta is cross sectional area by perimeter. So either rectangular fin you can write like this, and pin fin you can write it. Okay. Sagar Baba, I am not very sure about that. Okay, you can ask some civil faculty for it. Okay. Now, one more very special case that is not mostly asked, but still you need to know, when specified temperature at the end of the thing, yani ki they will give you at x is equals to L, T is equals to TL. They will give you a specified temperature. Then you can find out temperature distribution by using this equation, heat transfer by using this equation, where theta L is equals to TL minus T infinity and theta naught is T naught minus T. So you need to practice these new questions. Nowadays, you see, earlier they used to ask from the last 3 cases. Nowadays, they are asking from this case as well. So you need to remember these. You need to practice questions on these particular special cases. Okay. Chalo, let's go to effectiveness of fin. So what is effectiveness of fin? It is Q with fin and Q without fin. Q with fin and Q without fin. So without fin, it is basically HA T naught minus T infinite. T naught minus. So when you put the equations that we have defined for Q with fin, you will get effectiveness is equals to under root Kp by HA, and in this case it is tan HML under root HA by K. So as you can see here, this is also proportional to Kp by H. So what it is telling you that effectiveness is directly proportional to thermal conductivity. That means thermal conductivity of the material should be high. So you should use copper or aluminum. Also, it is inversely proportional to heat transfer coefficient. That means you need to use it with a fluid that has low heat transfer coefficient. For example, air. You should not use fins with water because they have high heat transfer coefficient compared to gases. Also, it is directly proportional to perimeter per unit area. That means you need to use thin and closely spaced fins. Now, let's go with the next case, unsteady state condition. Unsteady state. So in this we have three cases. First is system with negligible internal conductive resistance. By Biot number is given as R conduction by R convection. Now when we assume the conduction resistance it is negligible. Conduction resistance is negligible. That means the entire body is at the same temperature. That means A is infinite. R conduction tends to 0. Temperature is uniform throughout the body. And this is the analysis. This is the analysis. Hello. Hi. Okay. Now this is the analysis that is done under lumped heat capacity. Okay. This is the analysis that is done under lumped heat capacity. Lumped heat capacity analysis. Remember, when conduction resistance is 0, then you will say it is lumped heat capacity. Okay. Now in this case, Biot number must be less than 0.1 and temperature distribution can be given as where Biot number is, we already know it is HLC by K and Fourier number is alpha T time LC. Thank you, Dharamjeet. Okay. Now there is another case in which we say that surface resistance is negligible. Surface resistance is negligible. That means R convective tends to 0. R convective. And if R convective tends to 0 means H is infinite. H is infinite. Okay. By what is this? R convective is equals to 1 upon HA. Our area must be finite. If R convective tends to 0, that means H tends to infinite. That means whole entire surface will be at T infinite. And in this case, you cannot use lumped heat capacity analysis. You cannot do that. You cannot do. So what will you do? You have to assume the results by some error function. And they have asked these kind of questions. Here temperature distribution can be simply written as like this. But here temperature distribution is given by an error function. Temperature distribution is given by a error function. So you need to remember these equations. They are asking these kind of questions in which this x is basically the distance in this direction, alpha is the thermal diffusivity, t is the time, okay, and r is basically the radius here. Okay, so they are asking these kind of questions. You need to know what concept you need to apply to find out the answer. Okay, and finally we have both appreciable internal and surface resistance. Look, first of all, we have internal resistance as negligible. Then you use Biot number. When you have surface resistance is negligible, that means convective resistance is 0. Then you use error function method. But when you have both appreciable internal and surface resistance, then you are going to go and use Hassler chart. So Hassler chart gives you this Fourier number, this is Biot number, and Hassler chart is of course used when Biot number is greater than 0.1. That means lumped heat capacity is not valid. Lump heat capacity is not valid. You can use this equation and find out. You can basically use, and you can find out center temperature at any given time. Okay, time will be given. You can find out Fourier number, Biot number. You can find out this. You can substitute it here and find out temperature at any location. Okay, chalo. Let's go to heat exchanger analysis. Heat exchanger. So what are the assumptions? First of all, steady state heat conduction. Second is kinetic energy and potential energy is equals to 0. Specific heat is not a function of temperature. No axial heat conduction. Again, I told you heat conduction does not happen in axial direction. Only happening in radial direction. And outer surface is perfectly. So, when you apply steady flow energy equation, you are going to get MHCH minus ECI. This is your steady flow energy equation for a heat exchanger simply. Okay. Now for boilers, what happens? The cold fluid is evaporated. So for cold fluid, I will use this equation. Okay. What happens in condenser? The hot fluid is condensed. Okay. So here for hot fluid, I will use this. Okay. Now we can also use Newton's law of cooling. UA surface area delta Tm. What is delta Tm? It is log mean temperature difference. Log mean temperature difference. Now what kind of questions can they ask? They can ask you surface area. So this area you need to calculate. They can ask you the heat temperature of the hot fluid, exit temperature of the hot fluid. They can ask the exit temperature of the cold fluid. They can also ask diameter and. So we have two methods. First is LMTD approach. So LMTD is given as delta T2. For example, if this is parallel flow, so this is THI, THE, TCI. This is your delta T1 for parallel flow. So delta T2 for parallel flow. But what about counter flow? You have this kind of HI, TH, TCI, TC. This is your delta T1. This is your delta T2. Okay. So this, look, the equation remains same. For parallel flow and counter flow, the equation remains same. The only difference is the definition of LMTD. The only difference is the definition of LMTD. So here this is delta T1, this is delta T2. Here this is delta T1. What about multiple pass shell and tube heat exchanger? So in shell and tube, you will use the same formula that you use for counter flow. You just have to multiply it by the correction factor. So that's all. And correction factor will be given to you in question. Okay. Now what are some conclusions? LMTD is used when at least 3 temperatures are known. And fourth can be determined by using energy conservation. Now, very important point. Whenever phase change is happening for boilers and condenser, LMTD is parallel is equals to LMTD. But in sensible heating, LMTD of counter is always greater than LMTD of parallel. And therefore, area required for counter flow heat exchanger is always less than the area required for parallel flow heat exchanger. Now, in parallel flow, as you can see here, in parallel flow, your TC exit can never be greater than TH exit. But in this case, your TC exit can be greater than TH exit, can be greater. This is what it is written. And when CH is equals to CC, which is also called as balanced heat exchanger, both the specific heat capacities are same, then delta Tm equals to delta T1. Either anyone you can take, either delta T1 or delta T2. Okay, using L'Hospital. In general, delta Tm of counterflow is greater than delta Tm of force and delta T. Now, next is effectiveness and effectiveness, and it is used when only two temperatures are known and two you need to find out. So you cannot use LMTD method. So what will you do? The effectiveness is given as this: Q actual by Q, and Q max is always C min and delta T max. This is the maximum temperature difference. This is C min. So this denominator remains same. Numerator can be adjusted either for cold fluid or hot fluid. Now NTU can be given as QA upon C. QA upon C. Now NTU is a dimensionless parameter that gives you the idea of the bulkiness or the area of the heat exchanger. Now for any heat exchanger, effectiveness is a function of NTU and C. Now as you can see here, if you have double pipe parallel flow heat exchanger, it is given by this equation. But if you have a balanced heat exchanger, then this equation reduces to. So you need to remember this. And if you have a counter flow heat exchanger, then this is your effectiveness equation. But if you have a balanced heat exchanger, then it reduces to NTU upon NTU plus. Now whenever phase change is happening, yani for boilers and condensers, you don't have to worry about effectiveness formulas. Effectiveness or parallel flow is same as effectiveness of counter flow, and it is given by 1 minus E NT by like this. Okay, chalo. Now let's go to radiation. Let me have a sip of water. And then, so we have done conduction, we have done unsteady state conduction as well, we have done heat exchangers. Now let us move to radiation, then we will go to our convection part. Okay. Chalo. Now, the first terminology in radiation is radiation fluxes. You see, whenever you have an opaque body and G is the irradiation, that is incident radiation. G is what? Incident radiation flux. Now, because of its absorptivity alpha, it will absorb something. Because of its reflexivity, it will reflect some portion of G. Now, this body will also be at some temperature T, let us say, and because of its temperature, it is going to emit something, and that is emissivity. This is emissivity. Okay. How much it is going to emit? Emissivity into, and the both these portion, whatever is going out is called as radiosity. Whatever is going out is called as radiosity. So emissive power is due to its temperature. Radiosity is what? E plus rho G. That means this E plus rho G. Now whenever you have a normal body and anything is incident on it, then some portion will be absorbed, some portion will be reflected, and some portion will be transmitted. Now if you do an energy balance here, so you will get this, where rho is equals to, it is the fraction of the radiations reflected, it is the fraction of radiation absorbed, and transmittivity is the fraction of radiation transmitted. Okay. Now your first law is Planck's distribution. Now Planck's distribution gives you the spectral emissive power. What do you mean by spectral? That means at a particular wavelength. So it says that emissive power, spectral emissive power of a black body is a function of temperature and wavelength. So its simplified equation, it is a different equation, but its simplified equation is given like this. As you can see, it is a function of lambda and T. and C1 is the first addition constant, C2 is the second addition constant. Now, as you can see here, for a given temperature, you see, let us say we will fix this temperature. So, as your wavelength is increasing, first your emissive power increases. You see, first it is increasing and then decreasing. That means there will be a maxima somewhere. And when you keep drawing these curves, what you see is this: all the curves shift towards left. And when they shift towards left, what does that mean? It means that at a higher temperature, radiations will be emitted at shorter wavelength. So, for a given temperature, as wavelength increases, first of all, emissive power of black body increases and then it decreases. Okay? And as temperature increases, a large portion of the radiations emit at the shorter wavelength, then Wien's displacement law, it tells you that this product, you see, as temperature is increasing, wavelength is reduced, shorter wavelength, okay? The product of this, for any given temperature and wavelength, the product of this is. Then Stephen Boltzmann's law tells you that emissive power of a black body is equal to Stephen Boltzmann's constant into temperature 10 to the power 4. Temperature to the power 4. Stephen Boltzmann's constant is given by 5.67 into 10 to the power minus. And you will get it how? By you have this, right? You differentiate it with respect to all the wavelengths. So say you will get this. This you will get from Planck's law. Yes? And you integrate over the entire wavelength, you will get this. Then we have Lambert cosine. Now, Lambert cosine law says that for a diffuse body, if you have a diffuse body, always your incident at any angle, your radiations emitted at any angle is proportional to cos theta. That means this is equals to, this is dqn cos theta. This is equals to, that's all. It's a function of cos. And Kirchhoff's law tells you under steady state condition, net radiations at any surface of a body is equals to 0 and emissivity is always, for a black body, emissivity is always equal to its absorptivity. Okay? Chalo. Now it is the emissivity that gives you the relationship between a real body and a black body. It is given as emissive power of a real body divided by the emissive power of black body. So it tells you how closely your body is acting as a black body. And its value is between 0 and 1 for a black body. Emissive is equals to. Next is view factor. So view factor is basically the fraction of radiation leaving from one surface and reaching to the other surface. Okay. Now, what do we have? Some relations. First is reciprocity rule. Very important point, is always applied between two bodies. For example, even if you have three bodies, but either you will apply between 1 and 2 like this, or you will apply between 1 and 3 like this, or you can apply between 2 and 3. It will always be applied between two surfaces. So if, and it is given by AI Fij is equals to AFji. A1 F12 equals to. Okay. Next is summation rule. Now summation rule is always applied to one surface. For example, if you want to apply for I, so I can write Fi1 plus Fi2 plus Fi3 up to Fii Fin. For example, if you have this body, let us 1, 2, 3, 4. Let me apply with respect to 1. So I can write F11 plus F1 plus F1 plus F14 is equals to 1. It is always applied to only one surface with respect to other surfaces. Okay. Now let us say you have a plane surface. So always remember its view factor with respect to itself is basically 0. And when you apply summation rule, which is F11 plus F12 equals to 1, this is 0. that means F12 is also when you have a concave surface, concave, then F11 can be greater than F11 can be greater than 0. When you have a convex surface, so F11 is equals to 0 because whatever is going to emit here, it is not going to fall back on its own. Okay. Now next is symmetry rule. Symmetry rule. Now what is symmetry rule? You can apply it here. Like for example, if you cut this, these two sides are symmetric. So you can apply F Q 2 to 1. 2 to 1 equals to 2 to 3. You can also cut it like this. So these two surfaces are symmetric. You can write F1 to 2 equals to F3 to 2. So whenever you draw axis and bodies are symmetric, you can apply it. Then we have superposition rule. Now what is superposition rule? First of all, it is always used while splitting. That means I can say Fi and this whole body is J. So I can say Fij is equals to Fi to 2 and I to 3. Example, Fi to 3 equals to F1 to 2 and 1 to 3 plus. Okay? But remember one thing, it can never be used in converse. For example, I cannot say F3 to 1 and F2 to 1 is equals to F2 because it is converging. It is converging. It is not correct. It is not correct. It is always used in splitting. अभी तो heat transfer ही है. Then we will take applied thermodynamics. Okay. Let's move ahead. Now, what about concentric spheres? So, look, whenever you have two bodies, there are total 4 shape factors they can ask. F11, F12, F21, F22. That means I need at least 4 equations. By 4 unknowns, 4 equations I need. So, let's see. First of all, you have summation rule. So, this is with respect to summation rule is always applied through one body. Okay. So let us say for body 1 it is given by equation 1. For body 2 it is given by equation 2. Now I can also apply reciprocity rule which is applied between two bodies. So between body 1 and body 2 I can apply. Now I have 3 equations. I need one more equation. So you have to check for any other equation, any other boundary condition. As you can see, this is a convex surface, and for convex surface F11 is equal. So you have now everything. So F11 is equals to 0. That means F12 is equals to 1 by this equation. Then you can apply reciprocity rule. You can find out F21 and then you can apply this equation and you can find out F2. Everything you have found out. Same thing you can do for hemispherical as well. Okay. What about infinitely large parallel plates? Again, two bodies, two surfaces means 4 shape factors. In this particular case, F11 is equals to 0. F22 is equals to 0. The rest of the 2 you can calculate. If you have 2 infinitely long cylinders, so I can say F11 is equals to 0. This is not 0. F12 is equals to 1. Rest you can apply by using those equations that we have talked. If you have long symmetrical wedge, then F122 is equals to F221 can be found out by. There is one more special case here, which is long triangular duct. Now you see you have 3 surfaces here, 3 surfaces. When you have 3 surfaces, you have 9 shape factors. Okay. Now here, first of all, these are all plane surfaces. So F11 is equals to 0, F22 is equals to 0, F33 is equals to 0. This is okay. Okay. Now, rest of the things you can find out using this equation. For example, so this is what? If you have Fij means length of 1 plus length of 2 minus length of the third one, which is not there. Okay. For example, if you are taking 1 to 2, so L1, L2 minus L3, I2 L1. So this is how you can find out all of the A factors. For example, if you find out F23, you can write L2 plus L3 minus L1 upon 2L. This is how you can find out all of them. Now, net radiation heat transfer between two real bodies constituting an enclosure under steady state condition. You see, let us say this is one body and this is another body. So radiations are going from here, it is traveling from the space and reaching here. You can draw a circuit. This is the resistance. It is called as your space. This is called a surface resistance. Okay. Now this is called a space resistance. It is because of this. This is because of this surface first, and this is again your surface resistance, and this is because of this second surface. Because of this second. So similar to your conduction equations, you can write your heat transfer equation like this, and this can also be broken down into several parts. For example, you can only take this much circuit, or you can take this much circuit. You can take those resistances. So here this is your space resistance, this is your surface. Now you can modify your equations. You can modify this equation, this big equation you can modify it for this one, can be modified for particular cases. For example, if you have a small convex object in large cavity, that means A1, okay, A1 by A2 tends to 0 and F12 is equals to 1, it will be reduced. Now when you have two infinitely large parallel plates, so here A1 is equals to A2 is equals to F12 is equals to 1, you will get this. And when you have two infinitely long concentric, this, it can also be given for a sphere, and here it is R1 square by R2. You have to remember all these formulas. Now there is one more concept of equivalent emissivity or emissivity factor. So it is basically like overall heat transfer coefficient. So in every case, for example, in this case, your equivalent emissivity is equals to this. In this case, this is your equivalent emissivity. In this case, this is your equivalent emissivity. Okay. As you can see here, small convex body in large enclosure, equivalent emissivity. Two infinitely large parallel plate, equivalent emissivity. This. Two infinitely long concentric circle, equivalent emissivity. And then for spheres, equivalent emissivity. Hello. Now the last concept is radiation. So radiation is to basically reduce the amount of radiation between two bodies. So this emissivity must be very high, and this reflexivity should be very high. This reflexivity should be very high, emissivity should be very low of this circuit. And now because of one radiation shield that you have added, you have added three more resistance. One. That means without any radiation shield, you already had three resistances. When you added one shield, then three more resistances have been added. For every shield that you add, three more resistances will be added, in which two are surface resistance, one is space. So this is the total radiation that is resistances that are added because of one radiation shield. So rate of heat transfer with n number of shields can be given like, and if effectivity of all surfaces are same, then Q with n shield divided by Q with no shields is by 1 upon n plus 1. For example, if you have 4 shields added, then you can say Q122 with 4 shields equals to 1 upon 5 equals to 0 point of Q with no. That means the you have reduced your heat transfer or radiation heat transfer to 20%. Only now, only 20% heat transfer is happening because you have added 4 sheets. Chalo. Very well. So we have finished our radiation. Finally, we have convection. Finally, we have. So in convection, we start with force convection. And the very first dimensional number that you need to know is Reynolds number, which is inertia force by viscous forces, rho v LC by mu. Used to determine that if the flow is laminar or turbulent, forced convection. Forced convection. Next is Prandtl number. Prandtl number. Now, Prandtl number tells you if momentum diffusivity is dominating or thermal diffusivity is dominating. It gives the relationship between hydrodynamic boundary layer thickness, thermal boundary layer thickness. So it is mu Cp by K. Now, Prandtl number range for gases it is almost equal to 1. For oil it is much greater than 1. For liquid metal it is much less than 1. And for water it is 1.7 to 13.7. Next is Nusselt number. This is Nusselt number. So Nusselt number basically tells you which heat transfer is dominating. Is it conduction or is it convection? Okay, because you see every time conduction happens here. Conduction happens here. At the surface there is a fluid layer attached. So conduction is happening here. Then the upper layer is moving, so advection is happening here. Now conduction plus advection is basically. So out of conduction plus advection, which one is dominating? Okay. So it is HLC by K of fluid. K of fluid. So if Nusselt number is much greater than 1, then convection is dominating. If it is equal to 1, that means it is pure conduction. Pure conduction. If it is slightly greater than 1, that means conduction heat transfer is almost, convection is almost equal to conduction. But if they give you Nusselt number is less than 1, it is not possible. Because even if conduction is only conduction is happening, still it is greater, is equals to 1 basically. Okay. So the least value of Nusselt number can be equal to 1. Even if pure conduction is happening, no convection is happening. Okay. Chalo. Now ranges of H. So if you have free convection, so look, what is the order? You see, first of all, gases has the minimum, then liquid have more, and then phase change condition. Now in gases also, first we have free convection, then we have forced convection. In liquid also, first we have free convection, we have forced convection. Phase change we have boiling. This order you need to remember. This order you need to remember. So free convection, forced convection in gases, free convection in liquid, forced convection in liquid, boiling and condensation. This is the order you need to remember. Okay. Now, first of all, external flow. The first case is external flow, then we will talk about internal flow. Now, when you talk about external flow, then flow regime, that means if Reynolds number is less than 3 into 10 to the power 5 is laminar flow. If it is between 3 and 5 to 10 to the power 5, it is transition flow. If it is greater than 5 into 10 to the power 5, it is transition. The important point to remember here is if it is not given, then you will take these conditions, find out if it is laminar or turbulent. In question, when you solve question, you have to remember these values. If it is less than 5 into 10 to the power 5, it is laminar. If it is greater than 5 into 10 to the power 5, it is turbulent. Now, local heat flux and local heat transfer. So Hx can be find out. But you see, you can write out here Q conduction at y is equals to 0 equals to Q convection. By this you will get this equation and you can find out your local heat transfer. And then local heat flux you can find out Qx is equals to Hx area surface. Okay. Now what are the different solutions? So first of all, when we talk about isothermal flat plate, your hydrodynamic boundary layer thickness is given by Blasius equation 5x upon Reynolds number. Now from here I can see that Reynolds number is a function of x. If I put x here, your hydrodynamic boundary layer is basically proportional to root x. Then we have skin friction coefficient or local drag coefficient given by CFX 0.64 and is inversely proportional to root x. Now drag force till length x, is given by this equation, and it is average drag coefficient, and relationship between velocity boundary layer and thermal boundary layer was given by Paul Holson. It is given by hydrodynamic boundary layer by thermal boundary layer, Prandtl number 1 by. Now local Nusselt number is given by this equation 0.332, Reynolds number to the power 1 by 2 and Prandtl number to the power 1 by 3. Okay. And from here I can write this H, and I can see here H is inversely proportional to root x, like we have seen delta V proportional as we have seen. Now average heat transfer coefficient is simply when you integrate from 0 to x local heat transfer coefficient, and you will get 2hx. Also Nusselt number can also be when you put hx here, sorry, this hx here, you will find out 2 times of local Nusselt number. Similarly CFX is also 2 times of local skin friction. Now in turbulent flow we have this relations. This is your velocity boundary layer thickness, this is your local skin friction coefficient, local Nusselt number is given, and this is your average heat transfer coefficient, Nusselt number and skin friction coefficient. These values you don't need to remember. Turbulent they will give you, but still 1% if they do not give you, it is a very simplified version. At least you can remember this, at least you can remember these points. Now if you have external flow over cylinders or spheres, okay, so in this characteristic length is given by d naught basically outer diameter, okay, and if Reynolds number is less than 2 into 10 to the power 5, it is laminar. If it is greater, Reynolds number is greater than this, it is turbulent. Now flow consideration. Now you see, if you have this body and flow is coming like this, so at this point for example, you have this body and flow is coming like this. So at this point velocity will come to 0 and pressure will be maximum, and as this will move here, velocity will slightly increase, pressure will go down, and at certain point of time separation will happen. Now the separation for laminar flow happens at 80 degree. You see, this is 90 degree, it happens at 80 degree. Here it will separate. In turbulent flow separation occurs at 140, come till here and then separate. Okay. Also as you can see here at 80 degree your Nusselt number and heat transfer coefficient is minimum. For laminar flow, this is laminar flow. For turbulent flow is minimum at 90 degree. Now Nusselt number correlation. In this case Nusselt number will be given to you in question, but it will be a function of Reynolds number, of course, and Prandtl. And if you find out H here, you can substitute H here and you can find out heat transfer. Okay, now we have Reynolds analogy. Okay, so Reynolds analogy is only valid when Prandtl number is equals to 0 and it is given as Stanton number is equals to CFX by 2. Now next is Colburn analogy, and it is valid for all Prandtl number. It is given by this equation. So basically Reynolds analogy comes out from this only. If you put Prandtl number is equals to 1 here, you will get the same equation like this. Sometimes we mix both of them and we say Reynolds Colburn analogy. But remember, Reynolds analogy is valid only for Prandtl number is equals to 1, and Colburn analogy is valid for all the Prandtl numbers, Got it? Now Peclet number is given as Reynolds number into rental. Next is internal tube. Internal. So here, as velocity at a cross section continuously changes with respect to radius, we have no condition of mean free velocity. In internal tubes, it never reaches free mean velocity. Therefore, we have to find out the average velocity or mean velocity, and this is given by this. Now, mass flow rate is rho A mean velocity. Now, here Reynolds number is given by hydraulic diameter. How to calculate hydraulic diameter, I'll tell you in 1 minute. But this is range of Reynolds number. If it is less than 2300, it is called as laminar flow. If it is greater than 10,000, it is given as turbulent flow. But to solve in question, you will take this limit. If it is less than 4000, it is laminar. If it is greater than 4000, it is turbulent, simply. Now, hydraulic diameter is 4 cross-sectional area by perimeter. For example, in this, hydraulic diameter is given by di only. If it is annular, you can write d naught by di. D naught by di. If it is rectangular, then you can write out 4 area by perimeter. Area is what? This into this. Perimeter is what? 2a plus. Now, thermal boundary layer. Thermal boundary layer, when fluid is heated, it will be something like this, okay? So, temperature will change from Ts at the surface to a minima at the tube side. When fluid is cooled, it will change from Ts at the surface to a maxima at tube. Because here fluid is hot. Fluid is hot. Okay. Now again, there is no condition of mean free temperature or free steam condition, and therefore we need to find out average temperature. Average temperature. So this is my bulk mean temperature. Bulk mean temperature. And what is bulk mean temperature? It is a temperature at every cross section. Example, it is the bulk mean temperature at this cross section. This is the bulk mean temperature at this cross section. This is the bulk mean temperature at this cross section. And this bulk mean temperature keeps changing when cross section changes. Now, your fluid properties are taken at arithmetic mean of inlet and outlet bulk mean temperature. That means this is inlet, this is outlet. Then overall bulk mean temperature, your fluid properties will be taken at this temperature. Now, thermal boundary layer. Thermal boundary layer, it is the developed region in which this term is not a function of x. Because you see, temperature in developing region also changes with respect to x. Here also it changes with respect to x. You cannot say that temperature is fully. Now, H here in the developing region decreases. First of all, it is very high here, then decreases. And in the developed region, because heat transfer almost stabilizes, here H almost remains. H almost is the H profile with respect to. Now, what kind of question they can ask? Rate of heat transfer entire pipe. Entire pipe they are asking. So if fluid is heated, you can find out Q convection is m dot Cp. T B naught minus TB. B naught is the bulk mean temperature at outlet. This is bulk mean temperature at inlet. How to calculate bulk mean temperature? I'll tell you in some time. Fluid is cooled is m dot Cpi minus. If they ask you calculate heat transfer at any cross section यानी कि there will be a bulk mean temperature at this cross section and there will be a surface temperature at this cross section. So you can find out Hx Tx यानी कि surface temperature at this cross section minus bulk mean. Guys, these cases are going to help very much. If you just stick to these cases, you will be able to solve all the questions. You need to identify which case they are asking simply. Okay. Okay. Now we have two types of boundary condition in this. First is constant surface heat flow. For example, you have a pipe and there is it is just an example that a electric coil is basically wounded over it. And you are giving continuous electric supply. For example, 100 watt per meter square you are giving. So the entire surface, outer surface of pipe is covered completely by electric wire. And here Q is not a function of same Q you are giving at all the x. Second case is surface, constant surface temperature. Now here you have maintained a surface temperature. For example, you are condensing a steam over the entire surface. The steam will be condensed at 100 degree. That means the entire surface will be at 100. Okay. Now when you have constant surface heat plus condition, so bulk mean temperature will be by this condition. And rate of heat transfer in pipe, convection, m dot c, P exit minus T dot P. Now here you see, this I have already told you, your H graph. Now your bulk mean temperature will continuously increase. But this surface, this delta T will keep increasing in developing region. But here delta T is not a function. Delta T becomes constant. Okay. What about constant surface heat plus condition? Surface temperature condition. Surface temperature condition. So here mean temperature radiation is delta T Ts minus T. Okay. And this is your temperature distribution equation. It is exponential variation. Rate of heat transfer, you see here, this is your delta T1, this is your delta T2. You can find out LMTD, you can find out heat transfer by this equation. And this also you can use. Also can be. Also here delta T keeps changing. Okay, I told you surface temperature remains constant. Okay, but because this keeps changing everywhere, delta T remains changing in developed region. Now, Nusselt fully developed flow. All the relationships are given in fully developed flow. Okay. Laminar flow, constant surface heat plus condition. Nusselt number is given by this condition. Okay. Constant surface temperature, circular pipe, Nusselt number will be given as 3. For any other geometry, Nusselt number will be given to you in question. But if you have turbulent flow, mostly it will be given to you in question. If not given, you can use this condition. Now here N is 0.4 for heating and 0.3 for. What about developing region? Now in developing region also they do not ask you, but still there is a number called greatest number, and it is basically replacing, by in developed region you have Nusselt number. Greatest number replaces Nusselt number in developing region, and it is given by d by x Reynolds number into Prandtl number. And the flow will change to developed condition when Great's number is equals to 20. Okay, chalo. Here also Reynolds analogy is basically for Prandtl number is equals to 1, Stanton number is equals to F by 8. F is friction factor. Now Colburn analogy is for all the Prandtl numbers, and it is Stanton into Prandtl number equals to F by 8. Again, if you put Prandtl number is equals to 1 here, you will get the same equation. Chalo. Next is natural convection. So by natural convection, flow happens because of density difference. Now how the density changes with temperature is given by volume expansion coefficient beta. Okay, and it says that beta is equals to 1 upon rho del rho by delta T, and beta is also equal to 1 upon T mean. Now T mean is T surface plus T infinity. Now when you do dimensional analysis, what do we get here? Nusselt number is a parameter, is a function of Grashoff's number into Prandtl number, and this the product of Grashoff's and Prandtl number is given as Rayleigh number, and heat transfer in natural convection is given by HA Ts minus. Okay, now Grashoff's number. So Grashoff's number is G beta Ts minus infinity LC cube dynamic viscosity square. Now here T film, you will find out all the properties on this, and beta for ideal gas is given by 1 upon. Just now I told you. Always remember, always remember that T film is in Kelvin. If you do not put it in Kelvin, you will get wrong on. Always. Always remember, put it in Kelvin. Okay. Now, criteria for free or forced convection. How will you identify if it is free convection or forced convection? Okay. So, if there is no velocity, means free convection. If there is velocity, that means it could be free or forced. But it will be decided by Richardson number. That is Grashoff's number divided by Reynolds number ka square. Now, if Richardson number is much greater than 1, that means Grashoff's number is dominant. That means buoyancy effects are dominant over inertia forces free convection. If it is much less than 1, that means inertia forces, it is much less than 1 means what? Grashoff's number is much smaller than Reynolds number. That means inertia forces are dominating over buoyancy force convection. Is what? Force convection. When it is almost equal to 1, that means both have equal significance. Free and force convection equal significance. It's called as mixed. What are the different correlations? Nusselt number will be given to HLC by K, and it will be a constant Grashoff's into Prandtl number to the power n. And Grashoff's into Prandtl number is given as Rayleigh number. Rayleigh. Now n will be 1 by 4 for laminar and 1 by 3 for turbulent. Now, if you have an inclined plate, then you see this G. This you have G, right? This G will be replaced by G cos theta. Nusselt number. Very well. So, guys, we have done a lot. We have started with conduction. So, first of all, we talked about steady state. Then we talked about spins. Then we talked about unsteady. Then we went to heat exchanger. Then we went to radiation. Then we went to all the topics in the heat transfer subject is covered. And this will be I will share this PDF by Telegram group. If you have not joined my Telegram group, join the Telegram group. It will be very, very, very useful for you. If you just read it properly, if you apply all the cases, if you are able to identify what case they are asking the question, you will be able to apply the specific formula and you will be able to solve the question. Trust me. I know I have gone a little fast, but if you just go through this PPT, you will be able to identify all the cases that can be asked in the question. So make sure you go through the PPT. I'll share it in my Telegram group. Do join the Telegram group. Okay. And guys, congratulations to these guys. They have secured very good ranks in ESC. Okay. And other students are also there, but of course they are on the limelight. So congratulations to them. And guys, if you are targeting GATE 2024 and you are still in dilemma of what test series, what mock test series you can join, we have already studied our mock test series. You can join these test series. At least 8 to 10 mock tests you give for your exam. Just remember it. Okay. Hello, very well. So we can stop here. Thank you so much. Bye bye. I'll see you very soon. Okay.